Hello, I'm Nick Kramer, and today we're going to be covering beam bending and engineering structures. In aerospace engineering, there are a ton of objects that we want to model as beams. The antennas on satellites, the wings on a plane, continuum robots, the booms supporting the solar panels on the International Space Station, future robotic structures on the moon, or supporting orbital structures. To get going, let's start by defining what a beam is. A beam is a structural element that resists loads applied laterally across its primary axis. There are naturally different types of beams, and the most common way to define them is through the boundary conditions. The first boundary condition is a simply supported beam. This means that the supported points on the beam are not allowed to move but can rotate. Next is a cantilever beam. The cantilever beam is probably the most common beam type in aerospace engineering, with nearly all of our examples being cantilevered. What makes it so common is that one side of the beam is fixed in displacement and rotation. Finally, we have the fixed beam. It is similar to a cantilever beam, but instead of just one side being fixed, both sides are fixed, like you might find in structural support of a building. We showed some examples of things we model as beams, but it leads to the question, when does a beam stop being a beam? Some things are clearly not a beam. A cube, for example, is not a beam. But what if we make that cube a little bit longer? Is it a beam? How about this? When we ask these questions, we aren't just asking if it's a beam or not. What we're actually asking is it useful to model this as a beam? Which is a slightly different question. This reminds me of one of my favorite quotes from statistician George Box. Essentially, all models are wrong, but some are useful. We're not trying to model a beam in an attempt to perfectly replicate reality. Instead, we are trying to model something like a wing or an antenna as a beam so that we can decide, will it deform more than I can tolerate? When it starts to deform, will it still be pointed in the direction I'm interested in? These decisions don't require the model to be perfect or right, as was saying. They just have to be good enough to be useful. So, what are some ways that modeling something as a beam is no longer useful? Well, a dead giveaway is when two axes are constrained. In this case, we have both the primary bending axes and a secondary one constrained. Another indicator is when there are forces acting in two axes that will require bending parallel to the constrained axes. In this case, we can see that there's a load at the wingtip of the beam, but it varies parallel to the boundary condition. As we were exploring earlier, there's an intuitive understanding that as a beam gets shorter, we would expect it to act less like a beam. This is captured by the concept of slenderness ratio. The slenderness ratio is most commonly associated with columns which would be loaded in the axial direction, but is conceptually applicable to beam bending as well. The slenderness ratio of a beam is the length of the beam over the thickness of the beam in the beam bending direction. In this example, L is the length and A is the thickness. We can see that the slenderness ratio is 12. As we decrease the height of the beam bending direction, we can see that the slenderness ratio will increase, in this example going to 24. The general guidance is that slenderness ratio of 10 is about when you should be cautious using a beam model, though there are a lot of ways and situations where a beam with a lower slenderness ratio than 10 could be used, so it's not a hard and fast rule. Now that we've covered what a beam is, why we care, what types of beams there are, and when a beam stops being a beam, let's get into the modeling. The most fundamental equation of a beam modeling is the static Euler-Bernoulli beam equation. Because of its fundamental nature, it warrants us taking a deep dive into what it is, what its parameters are, what they mean, and their impact on real-world problems. Let's start by looking at a beam and defining terms. First, we need to identify the primary axis labeled x in this scenario. X is commonly what the beam axis is called. This is the beam's local coordinate system. Often there's a fixed rotation relative to the body frame of the object they are attached to, for example, a cube, satellite's antenna, or the wing of an aircraft. Next, we need to identify the parameter W, which is the displacement of the beam in the orthogonal direction to the beam axis, in this case, the z-axis. W is relative displacement from the neutral axis in yellow. This is important in cases like when an aircraft wing has dihedral and its undeformed neutral axis changes in the z direction along the x-axis, meaning that the z value and the displacement value w are no longer equal. Now that we've established the basic variables, let's take a look at the other constant in the equation. We will start with the second moment of area, referred to here as I, which is a function of x. First, we need to address why the second moment of area might vary with x. Let's take a wing as an example. We can take the airfoil cross-section along the wingspan, and when we compare them, we see that they are each different sizes. The sizes in this example decrease towards the wingtip like they might in an actual aircraft. The equation for second moment of area is the double integral of z squared with respect to the cross-section area, represented here as dy dz. We'll discuss the meaning of this equation in more detail another time, but suffice to say, it scales quadratically with the thickness of the cross-section. In our example, this means that the second moment of area is smaller at the wingtip and shows why it depends on the beam axis in its general form. Moving on, we are now going to focus on the modulus of elasticity. The modulus of elasticity is basically how stiff the beam is or how much the beam will resist bending. We can once again return to our wing, but now instead of just looking at the cross section, we'll look at what's inside the cross section. It's fairly common for airplanes to carry fuel in the root sections of their wing, meaning that the structure of the tank contributes to the wing cross sectional modulus of elasticity at that point. On the other hand, various points in the wing, there will be wing spars which will have a lot of material and will be more structurally rigid. This example demonstrates how the wing modulus of elasticity varies along the beam. Turning to the Euler-Bernoulli equation, we will next look at the distributed load Qx. Qx is the external force applied to the beam. To help us understand what that might look like, we'll look at a few different example load cases. The first will be a uniformly distributed load where the force is applied uniformly across the whole beam. This is similar to the that might be applied to a perfectly rectangular diving board subject to its own weight. The next example is a beam with a concentrated load placed at the center of the beam. This is similar to a beam that has something sitting on top of it. If you were to combine case 1 and case 2, you might be able to approximate the person on the diving board. Finally, let's return to our wing example. A traditional ideal lifting distribution for a wing is an elliptical one. This can be applied to our wing to estimate the amount of displacement it might have from the aerodynamic loading. Finally, it's time to start talking about the double derivative of displacement with respect to the beam axis, d squared w over dx squared, or the curvature. To understand the curvature, we should start with what the slope of a beam is. If we look at a deformed beam and pick an arbitrary point, the rate of change of the displacement with respect to the beam axis is the slope. The slope can be broken down into the vertical displacement from the neutral axis, dw, and dx, the change along the beam axis. This forms a right triangle with the slope of the beam, which we use to find theta, or the beam angle. The beam angle also represents the rotation of the neutral axis. Using small angle approximations, we can define the beam angle theta as dw over dx, and you often see it referred to this way. Now that we can visualize the slope of a beam, let's go back and start talking about how curvature fits into the Euler-Bernoulli equation. So, what is curvature? If we were to take a curve C in this case, and pick a point P on that curve, then we were to draw a circle that would fit the local section of the curve the best, it would have a radius r. The inverse of the radius of the circle is the definition of curvature. In a little simpler terms, curvature is how flat the curve is. The higher the value of curvature, the more curved the curve is. The smaller value of curvature, the flatter the curve is. Now let's take a look at how the curvature varies for curve C. We can see that at the transition points, the curvature is high and the radius is small. But at the flatter regions that are more easily approximated by a line, the radius is large and the curvature is small. Okay, so that's cool, but how does it relate to our beam? Well, let's start with the circle that is sitting on top of our beam, touching at point P on the beam. Now we can imagine that the displacement of the beam is actually in the shape of that circle, and the displacement W is the displacement distance between the undeformed beam and the deformed beam. With that in mind, now we can think of the equation of a circle as x minus h squared plus w minus k squared equals r squared, where h equals 0 and point P is set to 0, 0. This means that k equals r. Next, we can solve for w and take the derivative with respect to the beam axis x. Now we once again have the slope of our beam, but represented as a circle this time instead of a triangle. Then we can take one more derivative, d squared dw over dx squared, and we can assume that we are assessing the double derivative of w with respect to x, where x equals 0. This eventually gives us negative 1 over r, which, it turns out, is also our definition of curvature, which we use in the Euler-Bernoulli equation. Let's take one last look at how the curvature might look in comparison to the beam slope. We start by deforming our beam and drawing the tangent line to see how that assumed circle balances at our point, demonstrating the curvature of the beam. Wrapping up, let's go over what we've covered. We covered what is a beam, what beams are good for, types of beams, when a beam stops being a beam, and the Euler-Bernoulli beam equation.